So our last major topic today is going to be finding best fit plots. Okay. So let's go ahead and summarize what kinds of plots we've gone over. So we've gone over exponential. So what did exponential look like? Exponential looked like what? It could look like this if we had growth. I'll put it over here. Growth. Or it could look like this, right? If we had decay. We also had logarithmic. We didn't talk about that today, but we have talked about that, logarithmic. And that looked more like this, right? Kind of would start and then flatten out. We had logarithmic. We had, what was another one? We had power. We haven't really talked about those in a while, but we had things like x squared, x to the third, x to the fourth, x to the fifth, that kind of thing. Do you remember what x squared looked like? What did x squared look like? X squared kind of looked like a parabola. Something like this. We had x cubed. Kind of looked like that. These are not to scale at all. That's just the general shape. And then the other ones kind of follow that same pattern. And then we had linear. Right, so linear looked like what? Yeah, it's a line. So this is an increasing one. Or you could have a decreasing one. We're very excited over here. So we had exponential, logarithmic, power, and linear. So the idea is now you're going to look at data, so say your boss is like, oh, we've got blah, blah, blah data that looks like this. Now, do you think that that is linear? Or do you think it's exponential? Or do you think it's logarithmic? He's not going to ask you that, but he's going to say, we have this data, so what do we think is going to happen in the future? So, for example, you always hear people talk about, say global warming, And depending on how you look at the data, this is actually really important, because if you think that the, Earth is warming at a linear rate, then you'd say, oh, okay, maybe the data is going like this, and it means that, we got some problems, but they're not that critical. If you think that this is an exponential fit, then the problems are getting bad really, really fast. So that's obviously got its own implications. Alternatively, you might say, well, no, this data is clearly logarithmic, which means that it's kind of leveling out. So if I want to say, well, 20 years from now, we're really not going to be having that big of a deal. Now, the reason this is important is because the kind of data that you're looking at can really make a difference. So say we've got some data that looks like this, and, I don't know, I'll just draw an actual line. Like, say, if we're talking about global temperatures, I have no idea what they look like, but let's pretend that they look like this. That's what you hear a lot of geologists say, is that over time, you've got some spikes, and you've got some stuff like this. So right now, what you're looking at really does impact the kind of conclusions you're going to make. So if you're just focusing on this section right here, if you were just focusing on that, then it might be very, I don't want to say the word obvious, but, it might be, say, oh, well, look, it's perfectly clear that, our global warming is going up exponentially and we're all going to die. All right, so that might be the case if you look at just one section of data. So you've always got to be careful when people say, based on past data, it's clear that in the future the blah blah is going to happen. We're going to run out of cheese or whatever, because you've really got to look at what data they're looking at. So, for example, if you just looked at that, you might say, oh, clearly it's a, exponential function. It's getting worse and worse. Alternatively, you might say, well, what if I'm just going to look at this section of data? So, like in the 1970s, my dad said that, like, everybody was convinced we were going into the next ice age because temperatures were decreasing, because people were looking at these curves and they're like, oh my gosh, look, our temperatures are going to go down forever and ever. So, you've got that to look at. Come back. Alternatively, no, that's not going to erase. We'll just expand it. So, if you looked at all this, you might say, well, it's not exponential, it's not logarithmic. It's probably just, maybe linear. Maybe it's increasing a little bit over time. Or if you look at all the data, if you actually had all the data going back forever and ever, you might say, well, I think it's pretty clear that it's just linear, maybe going up a little bit, but not much. So,
Mommy.
It's fun to work when you have a toddler around. Okay. So we're going to talk about how you can do these different matches and figure out, you know, is this going to be a power? Is this a linear? Is this an exponential? Because again, the kind of model you pick and the kind of data you look at really is going to impact the kind of decisions you're going to make. So we're going to use our TI-84s to do this, although in real life, you know, people are going to use Excel or something like that. So let's look at this example here. So this is number of weight loss surgeries. So somebody would be trying to make a point based on this information. You say, well, in 2002 there were this many, in 2003 there were this many, So these points right here that I highlighted are just these points right here. So this graph over here isn't any different. It's just centering on the top of those bar charts. So what we'd like to do is say, well, what do we think? Do we think that this is linear? You know, do I think that the line really goes like this? You know, or do I think it's logarithmic? Do I think that it's kind of tapping out, that we're, you know, limiting eventually the number of surgeries, that it was increasing for a while, but now it's decreasing? Or maybe this is part of a trend and it's actually going up. You know, maybe this is a blip and something completely different. So, you know, there's all these different kind of options. If you're talking exponential, go back and look at this right quick. You'll see that, you know, the growth model here for exponential looks really close to, say, x squared or x cubed. So you as a person looking at the data, you're going to have a really hard time trying to decide whether it's exponential or some kind of a power, and it's just going to depend on, you know, what you're able to come up with. So I'm going to show you how to find all these different ones. So here's the deal. This is the first thing I want you to notice. Notice here that we're using x starting at 1. We don't actually start with t equals 0, t equals 1 like we have been on the exponential problems. Can you think about why we're not starting at 0? We've been spending a lot of time talking about this. What's the deal with that guy? That guy always has to be what? That guy always has to be greater than 0, right? If that guy is equal to 0, this function blows up. So we can't actually put in a value for 0 if we're going to try to figure out what kind of a fit this is. If we put in one of our values as 0, the whole thing's going to explode. So we actually start counting at 1. So we don't do that. We don't use the zeros. We start counting at 1. And you're going to just go ahead and do that. Even if you don't think you're going to use a logarithmic function, go ahead and start everything at 1 just so in case you decide to try it halfway through, you know, you'll get a good shot. So let's talk about how to do this on your calculator. Okay. So first thing you're going to do is you're going to go to Stat. And in Stat here in Edit, you see you've got List 1, List 2, List 3. We've only got 2 lists. Our 2 lists are here X, which is the number of years after 2001, and then Y is the number of weight loss surgeries. So we're going to enter in our X values, 3, 4, and 5. Then we'll hit the over button and then go to our list 2, which is 63, 103, 141, 171, and 178. So those are our 2 lists. So now what we're going to do is now that we've entered these lists, now we're going to run some tests on them. So let me kind of walk you through what we're going to do before we actually do it. So you're going to enter your lists. I'm glad I did this because I almost forgot to do something. You're going to enter your list in your calculator. You're going to do the analysis, and it's just pressing buttons basically. And then you're going to examine the R value. And the R value is called your correlation coefficient. And the idea is it's basically a grade of how good the estimate is, how good the fit is. And so the closer to 1, the better. So the closer to 1, the better. Usually they'll range from, like 0.83 to not 8, so to 0.999. So the closer it gets, so just because you get a 0.85, that's not good. An 85% in this case isn't good. You really want like in the 90s, hopefully over 0.95 to really get a good fit, to make you reasonably confident in your answer. But in order to get these R values, you have to actually turn something on your computer, on your calculator. So diagnostic on. I'll show you how to do that. Once you turn it on, it should be on forever and ever unless you clear out your calculator. So diagnostic on. So you're going to go to your calculator, and if it's already turned on, don't worry about it. How do I get back to the home page? I don't know. I'll just go over here. So my catalog button is down here on my 0. So I'm going to go second 0, and that'll pull up my catalog. So this is actually a list of all the functions in your calculator. And you go dum dee doo 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 doo, and you come down. Eventually, it's in alphabetical order. And I'm gonna keep going. Bum doo 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 doo. And I'm gonna find the word diagnostic on. I'm gonna turn it on. Bum 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 bum. Ba-da-doo bum, ba-da-doo bum. Oops, passed him. Come back. Okay, diagnostic on. So once you get to diagnostic on, hit enter. It's gonna say diagnostic on. You're gonna say yes, done. Now you should be set. You shouldn't have to do that ever again on your calculator, like I said, unless you reset your calculator. You'll know if you don't have it because you won't get an R value. Basically, if you don't turn diagnostics on, you won't get an R value. And you'll say, where's my R value? Oh, crud, my diagnostics aren't on. Okay. So there you go. So let's see then if our data is linear. So now we're on step 2, the do analysis step. So I'm going to say, all right, I'm going to go to stat. And I'm going to tab over to the calc button. Calc. Now here are all the different regression. This is called regression analysis. We're going to look at all the different ones we can do. So this one here is AX plus B. So that's a line, right? This is lin. Make sure you recognize that LIN is lin for line. LN, that's not line. LN is natural log. Okay. So I'm going to go to my lin reg. I like this one. I don't like this one. I want the AX plus B. So my linear regression. Now, every time you do these, you're going to fill them out the exact same way. What it wants is the first list, which is L1. So I'm going to go second one. That's L1, comma, L2, comma, and I'm going to, it's like, look at this list, now give me an answer in terms of y. So I want a y equals answer. So to tell it that, I'm going to go to the vars button, over to the y vars, because this would make total sense, right? No. Y vars, I'm going to hit enter, heaven knows why, and I'm going to hit enter again, and now I've got this, like I said, this is why most people use Excel, but we don't have it, and it's good enough to kind of get you the idea of what's going on. Linear regression, first list, second list, please give me my answer as a y equals, enter, and there you go. This is actually your answer. So I'm going to pull this guy off. So here is, this is your linear regression. So it's always going to give you a general form. Y equals AX plus B. I'm actually going to spread that out because I'm going to put the actual values in there. AX plus B. Okay. So my A value is 29.8. 29.8. My B value is 41.8. So my equation, if this is a line, that would be my equation. So now I could use that to estimate, well, okay, how many of these surgeries are we going to have in 2010? How many of these surgeries are going to have, later on? But this is your equation that should fit the data. Now, here is your R term, and this is your correlation coefficient of 0.976. So that's a pretty good fit. It's not perfect, but it's something. So that's our linear regression. So let's try another one. Let's try, go to stat, over to calc, and I'd like to try who knows, let's try a logarithmic. So maybe the trend is actually flattening out. So let's see if the trend is flattening out. So linreg L1, comma, L2, comma, now this weird comma, thank you, mycelial vars, vars over, vars, yes, vars, why, thank you, who knows, the only reason I know this is I looked it up. This is, so if you're like, why am I doing the Y? You're not alone. I'm not really sure why you're doing the Y, but it's just better. I think you can get away without it, but I wouldn't trust it. So, yes, now you hit enter, and there's your logarithmic regression. So the nice thing about these problems is that when you do this on the calculator, it's actually going to give you the general form to get started. So we're going to say, if this is a logarithmic, it's going to be in this form, y equals a plus b log of x. My value for a is 59.059. My value for b is 75.343. Like that. So that would be my equation for this data. And my R value is 0.992. So this one is better. This is probably a better fit. So if I wanted to, I could actually go in here and I could plot this. And I could say, okay, y equals... Oh, look, it's already in there. How exciting. Clear out that other one. But that's the equation for this fit. And I could say, okay, well, what does this look like? That's not very helpful. Let's see if we can mix with our x and stuff. Let me go from, I'm just guessing here, I have no idea what this actually needs to be. I don't really need negative values of y, because I'm not going to have negative people getting plastic surgery. So my values were in the, what range? Hundreds? 178 was my max that I had there. So I'm going to put in a 200. Be a 200 and, oh, what the hey? 250. Now what if I graph it? Okay, so you see there's my logarithmic curve. So actually I don't need negative time either, so I can mess with my window a little bit. My x-min can be 0 as well. I'll let my window go out because I've already got my x values go out to 5, so I'll let the x values on my plot go out to 10 and graph it. So they're saying that this is actually probably a closer curve than the linear curve, and that kind of makes sense. You know, if you look at this, you say, okay, well, you know, it kind of looks like it's falling out. But again, you know, you've just got to base it on on the answer you get. That R value is really going to be the best indication of what's going on with this. So this, given the two options, this would be the one that I would choose as being the better one.